Hey, 1127 students. The thermochemistry unit was, in my estimation, more difficult than some of what we've done in the past. And since our lab was your first exposure to the topic and this end of the semester is on its way, I thought I would just make a quick video running through how I derived the equations that were helpful for us to get through lab. And I want to try and take a slightly different approach than what I took in lab. And so you might remember that the three kinds of setups that we explored in the lab was first mixing warm water and cold water together in an effort to quantify to what extent our little calorimeter was taking up heat as heat was being transferred. It's not a perfect insulated system. And so by accounting for the extent to which your calorimeter is doing that, we can do more accurate thermochemical studies. And so the second part was having that calorimeter constant information in hand. We took some metal that we heated up in a water bath, dumped it into a calorimeter with cold water, and used that temperature change information to determine the specific heat of a metal. And then finally, we looked at the reaction of magnesium with a relatively concentrated acid and looked at the heat generated in that reaction. So taking it from the top, I want to try and explain each one of these setups for solving an equation based on what I've highlighted. That in any thermochemistry problem, we can think about something that is losing heat, and the quantity of heat that it loses is going to be equal and opposite to that which is gained by a number of things, possibly, but at least one. And so I want to talk through this. I tried to make a video earlier and kind of botched it in trying to check my work. So I just decided to write everything out this time. So what I have here, let me see if highlighting it makes it a little bit more clear on the screen. Not really. So if we start with this premise of that which is lost must be gained, and the sign convention just means what's giving it off and what's being gained. In the first example, we took 75 mils of cold water, 75 mils of water that we heated up, mixed them together in the calorimeter, and just found the highest temperature that was reached before it started to taper off again. And so in that situation, what must be losing the heat is going to be the hot water. So I could say Q subscript hot water as what is going to be on the left side of the equation. And then the two things that can gain the heat that the hot water releases is going to be the cold water and the calorimeter. So recalling that we can represent Q as a mass times a specific heat times a change in temperature, we can make those substitutions for both the hot water and the cold water. And then we can also remember that when we're talking about a calorimeter, we don't much care about this MS. We multiply them together and represent it as just a calorimeter constant, also known as a heat capacity, in contrast to a specific heat capacity, which I have denoted with a lowercase s. And so setting up the equation that way is all we need. Now, I think in class I showed how we could basically rearrange this expression to isolate the variable C calorimeter by itself. But you can see that it's not strictly necessary. And so if I replace the masses that we used recalling that we assumed the density was 1 gram per mil. So 75 mils, we just call that 75 grams for both the hot water and the cold water. The specific heat of water, it's really at 25 degrees Celsius and I think 1 atmosphere of pressure. But we are going to assume that regardless of temperature, the specific heat is going to be 4.18 joules per gram degree Celsius. That assumption is not rigorously true because specific heat does change with temperature, but it'll be good enough for an intro chemistry class and just getting basic concepts. Now, in an example that I just made up, the temperature at which the cold water and hot water come into equilibrium is 56.4 degrees Celsius. The hot water starts at 92.4 and the cold water starts at 24.3. We're going to assume that whatever temperature the liquid hanging out in the calorimeter is at is also going to be the starting temperature of the calorimeter. That's just going to be an assumption we make each time. And so, having said all of that, you can see on the line below that the only variable that is not defined here that we actually need to solve for is the calorimeter constant. And I've just labeled it C right here. And I think that if you pull out a calculator and do the same math that I did, you see that the left-hand side comes out to minus 11,286 joules. That passes the sanity check because we expect the heat that is given off by the higher temperature item is going to be a negative number. So that works out. We can divide both sides by -1 to get rid of the negative signs. And just remember, be careful with your signs because in thermochemistry, the sign convention is very, very important. And we can subtract the heat that is gained by the cold water, 10,063.35 joules, and ultimately divide both sides by 32.1 to solve for the calorimeter constant. And in my example, the calorimeter constant was 38.1 joules per degree Celsius. And that would be a fine value for a system that does not have perfect thermal insulation. Remember that the purpose of this part of the lab and thermochemistry that you would do in general, whether for just teaching purposes or research, you want to know how leaky your system is thermally speaking. A perfectly insulated system would be one where the heat that is lost from the thing at a higher temperature only goes to one place, say the solution that the reaction's happening in. So we can go to the second part now and recall that in this part of the lab, we took the same volume of cold water, took about 30 grams of an unknown metal, heated it up in a water bath for 10 minutes, not getting it wet, but having it in a test tube submerged in a water bath to get it warm. And we made the key assumption that when we measured the boiling water or warm water right as we took the metal out, we said that is going to be the starting temperature of the metal. And again, we can set up this problem with this same equation, that which is lost must be equal and opposite to that which is gained. And in this case too, instead of hot water, we still have a hot metal that is giving off heat. And what will gain the heat is, again, going to be cold water and the calorimeter. So Q is going to be ms delta T for both the metal and the cold water. And in this case, now we can say that the Q of the calorimeter is still going to be C delta T. But now, from the last problem, we actually have an experimental value for our calorimeter. And I just showed one worked example. Of course, in lab, we did 2 trials, and you could average them together, assuming they weren't wildly off. Maybe you did a third trial. And so you can see as we substitute all the values that we have, and I'll just remind you, so the example that I came up with was 30.213 grams of an unknown metal. And in my example, I rigged it up to where it should come up pretty close to what copper's specific heat is. We don't know specific heat of the metal. That's what we're solving for. I said that 26.7 degrees Celsius is the temperature at which everything came to thermal equilibrium. The metal started out at 99.8 degrees Celsius. Don't know why it's freezing on me. The cold water started out at 24.3 degrees Celsius, and the solution, or I already said the 26.7 bit. So you can see now, like substituting in everything that we know, that the specific heat of the metal is the only thing that remains to be measured. And so just like last time, in class, I showed you how you could rearrange to solve for specific heat of the metal, but in truth, we don't actually have to do that. So that's the line below. You see me calculating everything, and we find that the hot metal in this example is, oh wait, sorry, scratch that. we see that the water is absorbing 752.4 joules of heat that's been released, and the calorimeter is taking up 91.44 joules. So we sum those together, and we get 843.84 joules. So that must be the amount of heat that the metal gave off. So we can divide by the M times the delta T, and by dividing by that answer, so 2,208.57 gram degrees Celsius, we can find the specific heat. And in my fictitious example, I got a specific heat of 0.382 joules per gram degree Celsius. So those are the units of specific heat. And in my, I hope I noted it. So again, when I set this example up, I was trying to find something that was kind of close to copper. And copper specific heat is 0.386 joules per gram degree Celsius. So you can see that in this example, that would be really great for identifying my unknown as copper metal. So now I'll advance to the third example that we did. So remember, in this part, we were taking either sulfuric, nitric, or hydrochloric acid, taking about 150 mils of those 1 molar acids, weighing out about 0.5 grams of magnesium metal, adding it into the calorimeter, and looking how the temperature changed over time. And this example is a little different. It's the most interesting because we're actually looking at a chemical reaction. And I'm just going to focus in on the case where it would be working with hydrochloric acid specifically. So if we're using HCl, the reaction that we would actually be doing would be magnesium plus 2 equivalents of hydrochloric acid, and that would form hydrogen gas and the salt magnesium chloride. And just like I have framed it twice now, we can again define it as that which is lost is that it will be opposite and equal to that which is gained. Now, what's just a little different about this is we want to think about the magnesium in the solution, and there's going to be chemistry happening in the solution, but part of that solution is actually going to be where, like, the reaction is going to be contained in the solution. And that might be a little difficult to understand in the abstract sense, but we're basically going to leave the left hand undefined. Like, that's what we want to solve for. We don't want to solve for a piece of it. We don't need to replace it with ms delta T and solve for one of those component parts. But it will be the case that the things that gain the heat will be the solution itself or the calorimeter. Now, on the slides, we talked about how when we have a constant volume system, which we did, the volume's not changing, we can, by determining the heat of reaction and by figuring out how many moles of reaction we had, we could determine the enthalpy change in the reaction. And so we also defined the terms exothermic and endothermic, recalling that if delta H actually has a negative sign, we're going to say it's an exothermic reaction, being that heat is going to be released in the reaction. And looking down at my answer, you can see that it is. What else to say? I don't want to go too in depth, just in case it's not really relevant for you all. But really, when we say that delta H is going to be the heat of reaction over moles of something, we're really talking about the moles of reaction. And that is based on the stoichiometry of the balanced reaction that we're working with. So in the example, you'll notice that the coefficient in front of the magnesium is a 1. And what that means is when 1 mole of magnesium reacts with the HCl, that is the same thing as talking about a mole of the reaction happening. And you can see, hopefully by inference, that if instead we were talking about HCl, for a mole of reaction to happen, we would actually need 2 moles of HCl. And so the reason that we're using 1 molar acid and a little bit of metal in this case is to basically guarantee that the magnesium is the limiting reactant, such that when you calculate the moles of magnesium, that really is going to be the same thing as a mole of reaction. And if that doesn't make sense and it doesn't come up in the lecture portion, you don't need to worry about anything. Now, this too is a case where, since we're not actually solving for, like, we're not replacing the left-hand side with anything else, we're kind of just figuring out the right-hand side and noting that that is going to give us the heat gained by the surroundings, and consequently that must be equal and opposite to that which was lost by the reaction, generated during the reaction. The last thing I'll note is what comes after the next line, that when you're doing these problems, unless you're told the solution that you're working with, its density, its specific heat, you're always going to assume that it behaves like water. And I actually had the chance to show one of you in lab that if we measure out, say, 30 mils of 1 molar hydrochloric acid and then take that thing's mass, you can do density equals mass over volume and demonstrate that, yeah, that density really is close to 1 gram per mil. I think in our case it was like 0.998 grams per mil. And so that makes it easy on us to say that the heat of the solution is going to be given by the mass of the solution times the specific heat of the solution. And in those cases, in my fictitious example, I took 151 milliliters of hydrochloric acid, assuming a density of 1 gram per mil, you're going to get 151 grams. And the specific heat, we'll say it's just like water, so it's 4.18 joules per gram degree Celsius. In my example, we start at 23.9 degrees Celsius of the acid, that is. And after the reaction has taken place and we see the final temperature that is attained before it starts tapering off, it's got 38.7 degrees Celsius in my example. Again, I rigged it up to where it came pretty darn close to the actual values that we were using as theoreticals. So, using the same calorimeter constant from part 1 of this lab, you can see that I've just substituted my known values. And again, everything on the right-hand side is known. So you can see on the line below that 9,341 joules is gained by the solution. So the solution of 1 molar HCl gains that much heat, and that's what drives it heating up. And the calorimeter is going to take up about 564 joules. Summing that up, it means that overall, 9,905 joules was transferred from the chemistry itself to the surroundings. Now, in my example, we also took 0.502 grams of magnesium. So the molar mass being referenced, which off the periodic table is approximately 24.305 grams per mole. I can divide by the molar mass to find that we used about 0.0207 moles of magnesium. Thus, we can determine the delta H of the reaction by just doing Q of reaction over moles of magnesium, and that will give us this very large value. Before rounding off, I'll say minus 479,564 joules per mole. Often these values are big, and so we often divide by 1,000 to get it to the relatively smaller number, kilojoules per mole. So minus 480 kilojoules per mole is our answer. In this problem and the rest, I report the correct number of sig figs, and I just go with 3. And so to express it with the right number of sig figs, I would do minus 4.80 times 10 to the 2 kilojoules per mole. Again, that's an exothermic reaction, as we would expect. And that is all that I have for you guys. ClipChamp cuts me off at 30-minute recordings, and so I'm not going to separately review how we could alternatively determine a theoretical delta H of the reaction by using tabulated enthalpies of formation to determine what we would expect our delta H of reaction to be. And minus 467.2 kilojoules per mole was the theoretical value for the hydrochloric acid magnesium reaction, and you can see that this fictitious example I came up with matches pretty nicely to that. Anywho, hopefully this was helpful, and hopefully some of you put this up to 2x speed on YouTube, so it was not mind-numbingly slow. So be well, and happy studying for the finals that are coming up.